This video is about classification performance and naive Bayes. The performance operator and its numerous variants allow results of classification or regression to be calculated. Given known labels, the performance of a classifier against these can be seen, and various maths formulae are used to produce performance metrics. This is all handled by the performance operator. A typical example classifier is naive Bayes, which can predict nominal labels based on the values of regular attributes, and this video shows these two operators being used together for the simple reason it's easier to explain them together rather than individually. So we'll start with a naive Bayes overview. We'll run a classification process and look at various important things. Then we'll look at the performance operator and what it does, and also some variations on a theme based on different inputs, and that'll all contribute towards understanding the performance vector. So let's start with the process. So we have a process. It makes some data. The details don't matter. Basically, it consists of 70% of a data set being created as the training set, and the remaining 30% being created as a test set. The training set goes to the naive Bayes classifier, where a model is built. That model then is fed to apply model. It's applied then the model to the test data, and the output will be a set of predictions, labeled training data essentially, which goes to the performance operator here. We'll also then output various things, including the original training data, the predicted labels on the training data, the performance vector, and the model itself. Let's start by looking at the data. I'll set a breakpoint there. Basically, two example sets, a test set of 45 examples and a training set of 105 examples. It's a fundamental point that you must have, in order to make a performance calculation, you must know the right answer. So the test data has the correct answer filled in. In real life, if you were doing this on a real unknown test set, there would be no label. But in that situation, you obviously can't estimate the performance. You have to rely on the previous performance you've measured to decide if the model is doing the right thing. So an important point then, this test set has labels. These get used later on by the performance operator to calculate various things. You'll recognize that the data, it's the ARIS dataset. I've simplified it to have nominal values instead of numerical values. This is simply to make it a bit easier to explain how naive Bayes works. If we look at the training data, for example, let's look at the statistics view. You can see the label has 3 possible values, and you can also see that attributes A1 to A4, I've basically created 2 nominal values, 2 ranges for each attribute. It's range 1 and range 2, and I've labelled them differently because it's a common error to assume that if a value has the same name for a different attribute, it's the same thing. It isn't. So I've given these ranges names to reflect the attribute to which they apply. But you can see there are 2 possible values for each attribute. Next thing we'll do, let's run the process to the point where the model is created. So now we have, again, this is the training data and this is the naive Bayes model. So let's look briefly at how naive Bayes works. So what the naive Bayes algorithm is trying to do is obviously make a prediction for the value of a label given values of these attributes. Now obviously, thinking about it, if we had a huge example set with every possible permutation of attribute and corresponding label, you could just look it up. But obviously that would firstly defeat the point of building a model, And in general, that very quickly becomes intractable because the number of attributes could be large and the number of possible values could be large, and there just isn't enough space in the universe to write all these things down. There certainly isn't enough data. What you're trying to do is calculate the class given the attributes, and as I've just said, that's intractable for large attributes and large numbers of values. So using an assumption, namely that the attributes are independent of one another, and the application of Bayes' theorem, you can recast the problem from tell me the class given the attributes to be the probabilities of the attributes given the class. Now, it may seem confusing, but it works, and in the literature, naive Bayes does seem to perform relatively well. It has some benefits in that it's extremely rapid, and there's only one pass through the data needed to produce an answer, even when attributes aren't independent. So there's just something going on about how it works that leads to good answers. It's not perfect, but it's good answers. And as you can see, generally speaking, this data has nominal attributes everywhere. So clearly the algorithm is able to predict nominal values as labels, and it's taking nominal values as attributes, as the regular attributes. You can do it for numerical. In that situation, you model the distribution using, say, a Gaussian distribution, and then you work out how far each point is and turn it into a probability. Too much detail for this, so that's actually the reason why I used nominal values to explain how it works. We can do a quick worked example in a moment. I'm going to run this all the way through to the end now, and we'll look at the predictions combined with a model to see if we can get insight as to how it works. So here we go. So now, again, this is the naive Bayes model, and this is the training data used to build the model, and this is the result of applying the model on test data. The test data has a smaller number of examples, 45. So this column here is the prediction. These are confidence levels about each value that's possible, and you can see here's the label. So what the performance operator is going to do is do some calculations on this to give us some measures. Before we do that, let's just see if we can understand where the performance has come from. So if we start with the naive Bayes model, and what I'll do is put the test example set below it so that we can see what's going on. So if you remember, I said earlier that you can recast the question, which is tell me the probability given the attributes, into a different view, which is based on the probabilities given the class. And this essentially is what is shown in this table here. How to read this? This is saying when A1 has the value R1 for A1, the probability of getting Iris setosa is nearly basically 1. That's based on an assessment of all the data in the training set. If R1 for A1 is the value for A1, then the probability Iris versicolor is 0.67. By the way, I've changed the precision to be 6 decimal places so that certain things show up better. So given that model, what we can do, we can use it to see if we can work out how it's coming to its conclusions. And what we do is, if we look at these four here, A1 has the value R1 for A1. So what you do is you look up here, work out the probability that it's Iris setosa, and the way you do it is you multiply the probability that it's Iris setosa when A1 has the value R1 for A1, which is that there, and you multiply it by R1 for A2, which is the value for A2, which is this one here, and luckily this has all R1 for A whatever, so it's these first four. Multiply those four together, multiply 2 by the prior probability, which is the same for all of them, ignoring that for the time being. So multiply those together, you get a number about 0.45. The corresponding probability for RS versicolor is those four multiplied. This is about 0.06, I think. And finally multiply those four, and that's very close to 0 given those two. So essentially the ratio of those probabilities suggests that the most likely one is this here, Iris setosa, which is indeed what the prediction is. Second is Iris versicolor, and you can see that based on these confidences, that is indeed what the model is saying. It's saying that Iris setosa is most likely, Iris versicolor second, and Iris virginica not at all, almost. Anyway, if you go down these, you can, if you want, work them out yourself, but basically you don't need to because it does it all for you, and you end up with this example set here. So this is actually what the known label is in the prediction. So to get a sense as to what that looks like, we can plot a chart here. So what I've done is I've plotted the label, the prediction along the bottom, and the actual label that we knew all along the left here on the y-axis. And I've coloured the point in based on the label. And by adding a bit of jitter, I can spread the points out. So you imagine you're 1,000 miles up and you're looking down on the points, and they're all lined up. By putting jitter in, you're essentially looking down these, imagine them to be skyscrapers or something. Anyway, you can see that it's done a good job on Iris setosa and a good job on Iris virginica, but a less good job on Iris versicolor. And I'm counting 4 there, 6 correct there, and 5 wrong there. But and so this leads us to the performance operator, finally. So this is what's known as a confusion matrix, and it's showing that plot on the previous chart, but now represented as numbers. And this is a very common representation that you'll see, and this is what's known as a performance vector in RapidMiner speak. And you can see the numbers there. It got 15 of those correct, 15 of those correct, 6 correct for versicolor, 4 wrong, 5 wrong. And if we go back to the chart, I'm sure you can convince yourself that setosa versicolor 4. Yep, there you go. And this, you'll notice there's some things about the performance vector here. First of all, there's accuracy here. So this is showing accuracy. Accuracy is calculated by, that's simply how many were wrong subtracted from the total divided by the total. So in this case there are obviously 45 in the total, and there are 9 wrong. That leaves 36 correct. So the accuracy is 36 over 45, which is 80, or 0.80%. The individual rows and columns, again you can do a calculation here. So the class precision here for this Iris setosa is 15 divided by 19, and that will give you 78.95%. The recall statistics, they're done basically on the columns. So there are 15 in total and 9 wrong. Therefore 6 over 15 should be 40%. Now, performance vectors can get very involved indeed. If we go back to the design view, if I type performance in here, available operators, you'll notice a large number of performance operators. And I've used this one called performance here, but you'll see there are a vast range of them for classification, binomial classification, regression, counting the number of support vectors, cluster counting, cluster distance, density, and other things like that. You can even create your own. Very complicated, or can get potentially very complicated, and the performance one I'm using is the simple one that will do most of what you need, because it works out in the context of where you are what you need to do. So if I click on the performance operator, it has no parameters that are that you can easily change. The example weights one is an advanced one. Come back to that later. But to illustrate what happens if you change the shape of the data, I'm going to change the data itself and turn it into a binomial classification. And what will happen is that the performance calculations delivered by the performance operator will be different. So I'll do that by simply changing a macro. That's what I'll do. So I've done that behind the scenes. If I run it now, if we look at the data, now there are only two possible values that the class can take on. R is for Sickler, I is for Ginica. I've eliminated Setosa. And now the performance vector looks a bit different. It's now a 2 by 2 confusion matrix. And now some other performance measurements have appeared. So accuracy, precision, and recall are based on manipulations of the data here. Area under curve, that's to do with the receiver operation characteristic, which is based on sorting the prediction likelihoods. I won't cover the details of that here. The important point is whatever your data, whatever the shape of the data you have in terms of the labeled types, that will dictate the performance vectors that will be calculated for you, which makes life a lot easier, frankly. So I'll go back to the original. Let's briefly deal with these are the tabs. Description here, that's just a text description of what you're seeing. Kappa is another calculation, I won't go into the details. Let's also look at some other parameters to the performance operator. So the use example weights is an advanced parameter. I've never had to use it. It basically multiplies an attribute called whatever name you like, as with roll weights. It multiplies that by the results, essentially scales up the performance vector or scales it down. I've never used it. We'll also go back to naive Bayes. There was a parameter called Laplace correction. It's always advisable to set that to true. What that does is it makes sure that if we just run it again and look at the probabilities in the model, in this distribution table it is called, it's possible if you don't have enough data that some of these are 0. So that would there be 0. So if I turn Laplace correction off, these will turn to 0. I'll do that now very quickly. And what that means is that you can see there some zeros. That means when it's trying to do calculations now, a 0 might completely override a perfectly legitimate value of a probability for another value, thereby leading to false sort of answers. So Laplace correction is always worth turning it on. So let's just take stock. So what we've done is we've made some data, training and test, we've made a model, we've used the model to make some predictions, and we've measured the performance as to how well that is, given that we're sort of cheating, we know the answer. What we can now say is that as long as the data we then see that we genuinely don't know the answer to, we can estimate that we think there'll be an 80% chance it'll be right, given that our performance vector here says 80%. Now, as I'm sure you can see, there's many a problem in this, and this is the subject of other videos where we do cross-validation, and there of course is a whole raft of things to think about. But I'll leave it at that point, and what I'll do is I'll put the naive Bayes model up the distribution table, and I'll bring up the test data as I did before. So if you really are that way inclined, you can do some manual calculations to while away the long winter evenings. Okay. There we go.